This is Learning Assessment Problem 11.3. The problem-solving strategy here is that of three-phase balanced AC power circuits. In the problem statement, we are told that we have a three-phase Y-connected load, which is supplied by an ABC sequence balanced three-phase Y-connected source. There's a transmission line with an impedance of 1 plus J1 ohms between the source and the load, and the load impedance is 8 plus J3 ohms in each phase. We are told that the load voltage for the A phase is 104.02 at an angle of 26.6 degrees volts RMS, and then we are requested to determine the voltage necessary at the source to provide that load voltage. So the first step will be to draw an equivalent circuit for one of the phases in this system. So this is the equivalent circuit for the A phase of this problem. V sub AN on the left is the source voltage, and that's the value that we are to determine. We have the neutral line, and then we have the line impedance, Z line, which is 1 plus J1 ohms, the load impedance Z sub L, which is 8 plus J3 ohms, and then we were told that the voltage appearing across the load V sub capital AN is equal to 104.02 at an angle of 26.6 degrees volts. So the first step here will be to determine the phase current I sub A, and we'll use the AC Ohm's law to do that, and we'll need the impedance of the load in order to perform that calculation. So Z sub L is equal to 8 plus J3 ohms, which in polar form is 8.554 at an angle of 20.56 degrees ohms. Now we can solve for that line or phase current. I sub AA is equal to the VAN of the load divided by the impedance of the load. This will be equal to 104.02, and in polar form the answer will be 12.175 at an angle of 6.04 degrees amps RMS. So we have the phase current I sub A there. We now need the total impedance in the loop, including the load, so Z total will be Z line plus Z load, and that is equal to 1 plus J1 plus 8 plus J3, which is equal to 9 plus J4 ohms. And in polar form, Z sub T is equal to 9.849 at an angle of 23.96 degrees ohms. This is the total impedance that the source sees, including the transmission line and load impedances. Now we'll proceed with the calculation of the phase voltage at the source, V sub lowercase an. An will equal this total impedance Z sub T times the phase current which we've determined. So this is 9.85 at an angle of 23.96 degrees ohms times 12.18 at an angle of 6.04 degrees amperes, or V sub AN is equal to 119.97 at an angle of 30 degrees volts RMS. This is approximately 120 angle of 30 degrees volts RMS. So this would be the A phase voltage. Now we know that the VBN phase voltage will have an angle of VAN minus 120 degrees. So this will give us that VBN is equal to 120 for the amplitude, an angle of 30 degrees for the A phase angle minus 120 degrees volts, or VBN is equal to 120 at an angle of minus 90 degrees volts. Those will be RMS. Then the phase angle of the CN phase will equal the angle of VAN minus 240 degrees. This will give us that VCN is equal to 120 for the amplitude, 30 degrees minus 240 degrees, which is equal to 120 at an angle of minus 210 degrees volts RMS.